In previous few days we were discussing amplitude modulated signals, different type of amplitude modulated signals, their generation, their demodulation, etc. We have already discussed. Their relative merits, demerits, etc. are also discussed. Today we will discuss a very important block called phase lock loop. This phase lock loop has got many applications in communication system. It may be used as local oscillator, synchronized local oscillator. It can be used as FM demodulator, and various other applications are also there. Instead of going to the detailed analysis of PLL, we will try to understand this PLL with minimum effort. That means with the help of some arguments and considering the easiest possible block diagram of PLL, we will try to understand this PLL. The basic block diagram of PLL is like this. The basic components of this PLL is, the first component is VCO, second component is a multiplier, and the third component is a loop filter whose transfer function is H omega, sorry, HS, no, H omega, yeah. VCO is a voltage controlled oscillator. Its output frequency is dependent on the input voltage, and we can control the output frequency of the VCO by controlling the input voltage. Now if VCO input voltage is E0, then its output frequency can be written as omega c plus some constant into E0. This c is a constant, and this omega c is the free running frequency. This is the free running frequency. That means the receive frequency when E0 equal to 0. Frequency when E0 equal to 0. This is called the free running frequency. The operation of the PLL is similar to that of a conventional feedback system. In a typical feedback system, the signal feedback tends to follow the input signal. If the signal feedback is not equal to the input signal, then the difference is also called the error. So the difference will change the signal feedback until it is close to the input signal. So a PLL operates in almost similar principle, except that the quantity feedback and the compared is not the amplitude but the phase. That's the only difference. The VCO adjusts its own frequency until it is equal to that of the input signal. At this point, the frequency and phase of two signals are in synchronism. This loop filter is basically a loop filter, low pass filter. The XT is the multiplier output. So loop filter will eliminate the high frequency components of this multiplied signal, and it will allow only the low frequency component, which is the error. Low frequency component is the error, and it will allow this error to pass through this filter, so that that particular error can be used to control the voltage, control the frequency of the VCO. Here we have assumed the input signal to this PLL is A sine omega ct plus theta I, where theta I is the initial phase angle of the incident wave, and the VCO output has got a signal of B cos omega ct plus theta 0, where theta 0 is the phase angle of this VCO output. So now let us try to understand the basic working principle. Basic working principle of PLL. Now it is not necessary for the VCO input and output frequencies to be equal. All that is needed is to set VCO free running frequency as close as possible to the incoming frequency. If the VCO output, this one, is say B cos omega c cap t plus theta 0, we can express this signal as B cos omega c t plus theta 0 cap, where theta 0 cap equal to omega c cap minus omega c t plus theta 0. That means if there is change in frequency, that change in frequency can be written in terms of change in phase. That is why it is called phase lock loop. So whether the frequency is different or phase is different, everything can be expressed in terms of its frequency. So when we say that the two signals has got different phases, it may happen due to the change in phase or change in frequency, or difference in phase or difference in frequency. So now let us see what happens at the output of the multiplier. So xt is the output of the multiplier, this one, that can be written as A into B sine of omega ct plus theta I cos of omega ct plus theta 0. Using trigonometric notation, trigonometric manipulation, we can write sine of theta I minus theta 0 plus sine of 2 omega ct plus theta I plus theta 0. The frequency of this last term is twice omega c. So obviously this high frequency component will be suppressed by this loop filter, and the loop filter will allow only the lower frequency part, this one. So output E0t, E0t also called the error voltage, is equal to AB by 2 sine of theta I minus theta 0, that is equal to AB by 2 sine of, say, theta E. Theta E is the phase error, where theta E equal to theta I minus theta 0. Let us see how this theta E and E0 are varying. So E0t equal to AB by 2 sine theta E. It is a sinusoidal function. So it will vary in this way, just like a sine wave. Something like this. Now suppose that the loop is locked. We are now trying to understand the lock procedure, how it gets locked. To understand this, first we will consider what happens when the loop is locked, and then we'll try to understand if the signal frequency or phase changes little bit, how this circuit or the feedback system makes necessary changes to make the system again locked. So first we will consider that the loop is locked. That means the frequencies of both the input and the output sinusoids are identical. So that means it is in steady state, and these three parameters are actually constant right now. So suppose under this condition the operating point is this, say at point A, corresponding theta E is this, corresponding E0 is this. Now assume that the input sinusoidal frequency is suddenly increased. That means the input frequency, which was originally omega c, becomes omega c plus some value, say k. That means now the incoming signal frequency becomes a sine omega c plus k t plus theta I, that is equal to a sine omega c t plus theta I cap, where this theta I cap equal to k into t plus theta I. That means if, let us use this type of notation, omega c is increased, because of that theta I will increase. Incoming frequency omega c is increasing. That implies that the phase of the incoming signal is increased little bit. Since theta I is increasing, this one is increasing, so theta E will also increase. That implies that theta E is also increasing. Now if theta E increases, the operating point was here. If theta E increases, corresponding error voltage will also following the sine wave. It will appear here, say at point B. That means the error voltage will increase from E0 to some other value, higher value. Since E0 is increased, so theta E will increase. That implies that E0t will also increase from its original value E0 to some higher value. Since E0t is connected to the VCO input, so the VCO input voltage is increased. That will increase the corresponding frequency, original frequency of omega c. So VCO frequency will also get increased. That means originally we have assumed that the input frequency was increased. Input frequency was increased, and now because of this feedback system we are seeing that VCO frequency is also increased. In the same manner, just like this one, that means the VCO will be again locked. So whatever change takes place in the input frequency, the same change will take place in the VCO frequency as well, to get the signal again locked. Similar thing happens when, instead of increasing the frequency, if the input frequency decreased, in that case the reverse thing will happen. That means the operating point will not shift it to the higher value, it will shift towards the lower value. So if frequency is decreased, the operating point will go in the reverse direction, so the error voltage will be reduced, and since error voltage is reduced, the corresponding VCO output frequency will get reduced, and the signals or the PLL will be again locked. So all the things will be just reversed when the frequency is decreased. So we can say that the PLL actually tracks the input signal. Now the two signals are said to be mutually phase coherent or in phase lock. The VCO thus tracks the frequency and the phase of the incoming signal. A PLL can track the incoming frequency only over a finite range of frequency shift up to this point, from this point to that point. So this range is called the hold-in range or lock range. So this range is called the lock range. Again, if initially the input and output frequencies are not close enough, the loop may not acquire lock. The frequency range over which the input will cause the loop to lock is called the capture range. So let us consider an hypothetical experiment with PLL. In this experiment, what we do, first we'll increase the incoming frequency from lower value to higher value, and then we will decrease the incoming frequency from higher value to lower value. So let us see what happens when the frequency is increased from lower value to higher value. That means it is moving in the positive direction. High frequency, this is the frequency. So in this frequency is in this direction. So first of all, up to this point it is unlocked. At this particular point, at frequency say f1 L, it gets locked. So once it is locked, we will designate this locked condition with discontinuous line. So if we increase the frequency, it will get locked. At certain point of time, suddenly it will release the lock at frequency say f1 H, and then if we increase the frequency, it will be again unlocked. So this condition is the locked. Now let us see what happens when we decrease the frequency, incoming frequency. So first, starting from high frequency range, it will be unlocked. So we will decrease the frequency, and at certain frequency suddenly it gets locked. At frequency f2H. Note that f1H and f2H are not same. Now if we decrease the frequency further, it will be under locked condition. It will cross f1L, and then it will suddenly unlocked at frequency say f2L, and once it is unlocked, it will remain unlocked in this way. So this is the hypothetical experiment. Now if we try to understand this lock range and capture range, if we start from locked condition, if we reduce the frequency, it will be locked up to f2L in the lower range of frequency, and from locked condition, if we increase the frequency, it will remain locked up to f1H frequency. So this range is the lock range. Now to understand the capture range, what is that? Starting from unlocked condition, if we increase the frequency, the first lock condition occurs at frequency f1L, and starting from unlocked condition from higher frequency, if we reduce the frequency, it will get locked at frequency f2H. So f1L to f2H, this range is called capture range. This is lock range. This is a kind of, you can say, an electronic inertia. Now in this simple analysis of PLL, we have assumed this theta I and theta O, theta 0, theta I and theta 0, and obviously theta E to be constant. Now if we assume that these phase are not constant but they are varying slowly with time, then the angle theta 0 tends to follow the input angle theta I closely when the PLL tracks the input signal, and the difference theta E is either a constant or a very small number. Theta E, either it may be a constant, almost constant, or very small number that is tends to 0, very small number. Now if the input sinusoid is noisy in nature, the PLL will not only track the sinusoid but also cleans it up. That means if this signal consists of along with certain noise, then the PLL will track this particular signal and it will eliminate that the added noise will not get tracked. So if there is some added signal here plus NT, that NT will not be tracked by this PLL. That means here we will get pure sinusoid like this one, and this NT will be eliminated from this. That means PLL can also be used as, that means it cleans up the input signal. It cleans up the input signal from the noise. Now PLL can also be used as an FM demodulator and frequency synthesizer. Frequency multiplier and dividers can also be built using PLL. The PLL it is relatively inexpensive integrated circuit, has become one of the most frequently used communication circuit. So this is very important as per communication is concerned. A lot of applications are there. So we tried to understand this PLL with minimum amount of mathematical analysis. We tried to explain it with the help of some arguments.